Hello guys, welcome back to Maison African Motives. Still working on our revisions for engineering science N3. We are going to be focusing in this platform, this paper, which was written in August 2023, which is an X paper. So we are not gonna waste much time. Remember what I always say, make sure that you have the required requirements of the paper, which is the properties of the water and steam. In this case, whereby you're working with the steam table. So you'll be given as part of an exam. And also, you're supposed to make sure that you read the instructions as you are answering your paper. It's very, very important for you to understand the instructions. Here we are given the instructions and information of the paper, answer all the questions. And what is important is to number the questions accordingly, and also the steam tables to be supplied by examination center. So you are supposed to be given this part here by the examination center where you are writing. You are supposed to have your steam table in that case. So we are not going to waste much time. We are going to quickly rush through our questions so that we see how we are supposed to attempt such typical questions in this case. All right. So the first part that we're given, which is question number 1, let us try to figure out how we're supposed to attempt that typical question. We were given the first part, which was to define the law of conservation of momentum. We have got the conservation of energy. We have got the conservation of momentum. So there are so many things that we are going to conserve, but when you are referring to momentum, what is it that we are talking about? That is that is the question. All right. So we'll be talking about the external forces. If there are no external forces that are being applied on the system of objects that collides, then we are going to see that the total momentum is going to remain the constant, just like what we have in energy. So in this case, let us just try to have it in writing. So we are simply saying if no external, let me just try to write it here. If no external force X, or it can be forces, or it can be just a force, in that case X on a system. All right, that's X there on a system. All right, of objects on a system of objects, in this case that collides. So we are supposed to have the colliding part, in this case that collides. The total momentum must remain constant. All right, the total momentum is going to be constant. The total momentum will remain constant. All right, so that's the condition there, will remain constant, meaning to say we are not going to have any change that is affecting, as long there is no external force that is being applied. We are not going to have any part that is going to change or affect our momentum. It is going to remain as it was. Taking on question 1.2, I talked about this type of a question. If you were revising, actually, for those who wrote before, it's fine. Just check how you're supposed to answer these questions. But if you are to check, we talked about this typical question. We are given the velocity on this side. We are given the time in seconds, or velocity in meters per second, though you're not given the units there. All right. So the graph above shows the velocity time graph. The most important part, guys, is yes, it's a velocity time graph. I want you to understand this and be careful, because it is affecting us as we are answering the same question that we are used to when we are dealing with our motion. We have a condition that we are just given a velocity time graph, let's say of a certain object, which is not a condition of a free falling. This part here is the one that is important. It's a free falling object. Just like we put a certain object here, then it falls down. As long you are dealing with a free falling object, it means you are going to consider on that condition the issue of acceleration, which is you are going to consider the issue of gravitational acceleration. That is going to be the major thing. You are going to consider the issue of what? The gravitational acceleration. Gravitational acceleration. This is the most important part that you are supposed to put into consideration, because we're talking about what? A free falling object. We are supposed to be considering the gravitational acceleration. That is the most important part. So we are not going to have a condition whereby we have the normal acceleration that we are used to. No, we are going to be using the acceleration as g in this case, which is our gravitational acceleration. That is of what? Of 9.8 meters per square second, as given from the information sheet of our paper, which is 9.8. So that is the most important part, guys. All is going to remain as before. The way that we used to calculate, everything is going to remain as before, but don't expect to be given any acceleration or to be asked to calculate acceleration on this type of a question, because it's a free falling object. All right. So it is given thrown at t is equal to 0, which means we're talking about time from t, which is 0 to k up to 7. All right. So the first part of the question on this was to calculate or to determine the value of k. So k is just representing the time. If you check here, this is simply the time at a certain point. So in this case, we had got the application. Remember from our linear motion, we said if you are given the object where it is starting from, which is the time, and the initial velocity, in this case, we've got the time at 0 in this case. This is the time that we started from our initial point. But we want to know now the difference that is there between, meaning to say from 0 to t, which is the value of k. So our time is represented by k in this case. So we are simply calculating the time in this case. By calculating time, we are calculating the value of k. The time between from 0 up to k is k minus 0, which is k, t minus 0, which is t. All right. So if for the time, that is the one that we are supposed to calculate. We do not know this value. All right. So let us check what we are given. At this point, we've got our initial velocity. We started at this point. This is our initial velocity at 16. So we've got an initial velocity there of 16 meters per second. And this point at t, which is k, is corresponding to the final velocity in this case. So we've got the final velocity of 50.3 meters per second. This is the information that we have. And we are supposed to calculate k, remembering that we are working with the gravitational acceleration in this case, which is equal to what? 9.8 due to a condition of a free falling object. So our gravitational acceleration is going to be used in place of our acceleration that we are used to. All right. So this part, we are going to apply our formulas from linear motion. Remember, we've got formulas that we can apply, but consider the formulas where there is u, there is v, and there is a, and we are supposed to calculate t. So if we check from our formula sheet, we've got v, which is equal to u plus at. That is the best formula that we can use. We can't use the formula of s is equal to ut, this and that, because we do not have the s in this case. So any formula that has got s, we cannot be able to apply it. So we are going to apply this formula, but like I said, A is representing what? Our gravitational acceleration. That is the condition there. So we are going to have this formula as V is equal to U plus GT. Our T is the value of K that we are supposed to calculate. So we can just write this as K, because we are saying this is time, but the time is represented by what? By K. So you can substitute our values, or you can make K the subject. It's up to you. So V, the final velocity of 50.3 is equal to U, the initial velocity of 16, plus the gravitational acceleration of 9.8 times the value of K, which is the value of T. So calculating K, guys, we are calculating the value of the time. That is the condition there. So we can transpose the 16 to the other side so that we can subtract. That's 50.3 minus 16 is equal to, you're going to remain here with 9.8K. So you can subtract these two values from your calculator. You're going to obtain 34.3, which is equal to 9.8K. So divide both sides. by 9,8, divide both sides by 9,8. You're going to obtain the exact value of K, representing our time in this case. So the K was going to be equal to 3,5. So in terms of time, we are saying our time is 3,5 seconds in this case. This is the time. But in terms of the value of K, we are just going to write K is equal to 0,5, 3,5, sorry. So this is our K at this point here. So meaning to say here, we have got 3,5. So that's half up. As you can see, it's half of to this point. So it means it accelerated within the first 3,5 minutes and maintained for the rest of the for the remaining 3,5 here from 7. From 3,5 up to 7, that's 7 minus 3,5, which is 3,5. In between here, it was maintaining a certain speed of 50,3. This part, there is no acceleration. We are maintaining the speed. We have a uniform velocity in this case. All right. Then 1.22, it was to calculate the displacement of the object after 7 seconds, meaning to say this whole part here, we are supposed to calculate the displacement, knowing that displacement can be calculated from area in this case. Remember, displacement from area. So we've got, it depends with how you're going to play around with your question. But like I said, guys, this part here is simply showing us a trapezium in this case. The first part here is a trapezium, and we have got a rectangle in this case. So you can use two shapes in this case, or you can divide this into a triangle like this. We have got a triangle, a rectangle, you combine them together, which means you're going to have 3 shapes, or you can work it as a trapezium. So I'm just going to use the whole trapezium. In this case, I'm just going to apply the whole of this trapezium here, the whole trapezium and a rectangle. Okay, so that is how to calculate the displacement. You can use the area in this case. All right, so you're saying 1.22, the displacement is equivalent to area. So the displacement is equivalent to area under the graph. So the area under the graph, we've got the area of a trapezium. Area of a trapezium is half sum of the parallel sides, that is half of A plus B times the perpendicular height. Then we also saw that we are going to remain here with what? A rectangle, and the area of a rectangle, it's length times breadth, or length times width. It's one and the same thing. So when you are dealing with a parallelogram, I mean a trapezium, now I'm referring you to a wrong shape. When you are talking about a trapezium, from our mathematics, guys, we say this part is taken from the 2 sides which are parallel. This side parallel to this side. So this will be your A and this will be your B, the sides that are parallel. And this is the one that we are referring to as the perpendicular height. If you are given your trapezium, in this case, in this format, if you are given a trapezium in this format, in this case like this, it means the sides that are parallel will be this one. This will be your A, this will be your B, and this will be your perpendicular height. It must be at 90 degrees. So that's how you calculate the area. Half sum of the parallel sides times the perpendicular height. Half sum of the parallel sides times the perpendicular height. So in this case, let us consider the sides that are parallel. The sides that are parallel in this case from this trapezium is this side and this side. And this is our perpendicular height, the length here, which is the difference from this point to this point, remember, is 3,5. And from this point to this point, it's 16. It is corresponding at 16. And here, it is corresponding to 50,3. So we've got 50,3. So these are the sides that you're going to add, the sides that are parallel, 16 and 50,3. All right, so it's going to be half of 16. So let's have this as half of 16 plus 50,3 times the perpendicular height in this case, which is the one that is perpendicular to the ground, which is 3,5, the difference here. So that's a 3,5 there. So we are going to have this as 3,5, okay? Then we move on to the rectangle, plus we move on to the rectangle. The rectangle is affected by the length and the breadth, or the length and the width. So in this case, we are going to take this side and this side. So we've got length and the breadth. So from 7 to from 3,5 up to 7 is simply a difference that you're going to make 7 minus 3,5. And if you subtract this, you are going to obtain 3,5. So meaning to say in between here, there is a difference of what? Of 3,5. So we've got the length and the breadth that you're simply going to multiply 50,3 and the 3,5 in this case. So these are the ones that you're going to multiply together. So we've got the 50,3. That is the side here is going to be 50,3 times 3,5, which is simply the difference that we had between the points. So we are going to simply combine everything now from this part. We are going to obtain 116,025 plus you combine this side, you're going to obtain 176,05. So that is the distance. We are simply talking about the distance between the first points and the distance on the other point. So you combine, but you're calculating it as area. The area that you're calculating represents the displacement. So that is how you're going to have. So you're going to combine this, which is 292,075 in meters, not square units, because it's displacement. Yes, you are calculating area, but what is it representing that area? It represents what? The displacement. So you're supposed to write the units in meters in this case. So you're supposed when working out these typical questions. Actually, it's not like you are limited only to the use of the area. You can even apply the laws that, as long as dealing with the linear motion, you can apply any equivalent part, any part that is equivalent, but mostly for not to have confusion, the best part is to simply use the area. But I shall talk about other formulas as we are moving on, so that at least we can see how to work out this, which is also best for us to join the membership family. By joining the membership family, you'll be able to access some of the other formulas that can be used as we are simplifying. So make sure that you join the membership family, guys, also to support our movement as we are having this program. Anyways, let us see the other part on 1.3. We are given the driver pulley, in this case of an electric motor, has a diameter of 12 centimeters. So this is the information that you're given from the driver pulley and rotates at 20 revs per second. It drives a pulley with a diameter of 200 millimeters. So we are talking about the driven. In this case, we've got the driver and the driven. Then the tensions in the belt are 600 and 300 in this case, right? So this is the information that you're given. So remember that the tensions taken, the driver is the one that is going to have the bigger tension, which is from the driver, which is T1. So we've got T1, and we have got the smaller part, which is what our T2 on the slack side in this case. All right. So the driver, I'm just going to write it in terms of 1. You can write in terms of A and B, 1 and 2 to indicate the driver and the driven. It's up to you guys, that part. All right. So you're going to choose what is best for you, but I'm just going to use 1 and what? 1 and 2. So as we are told, we've got the driver and we have got the driven in this case. All right. So on the driver, like I said, I'm just going to use 1 for the driver. All right. So this is our question 1.3. So for the driver, I'm just going to denote with 1. And for the driven, I'm going to use the denotation 2. All right. So that's it, guys. Let's check. The driver in this case is given at diameter of 12 centimeters. So we've given the diameter and the rotational speed of 20 revs per second on the driver. So meaning to say on the driver here, we've got the diameter. So we've got the diameter in this case of 12 centimeters, which you can convert to meters, divide by 100, which is going to be 0.12 in meters. And also the speed, we are given the rotational speed, that is n in revs per second, 20 revs per second. And okay, let's check. That's what we are having for now. And here we have taken this and this speed. It drives a pulley with a diameter. So this is now a driven. It's now driven. So the driven one, it has a diameter of what? 200 millimeters. It drives. So the one that is that the driver, it drives what? a driven. So that is the condition there, guys. Okay, so on the driven, we are given the diameter. So I'm just going to use 2 there for the driven, which is 200 millimeters. So we've got 200 millimeters. To convert to meters, divide by 1,000. Milli means times 10 to the exponent of -3. So you multiply by 10 to the exponent of -3, or you divide by 1,000, which is going to be 0.2 meters in this case. Okay, that's it. Rotating at, so we are given the rotational speed of okay, sorry for that, I'm taking from the wrong person. Okay, so we are here. Okay, so 200 millimeters, and the tensions in the belts are 600 and 300. So we've got T1 for the driver and T2 for the driven in this case. So the T1 being 600 Newton, and T2 in this case being 300 Newton. All right, so make sure that you have got the information. Okay, then with the information, it'll be easier for you now to answer the question. The question is calculate the rotational frequency of the driven pulley. The rotational frequency is the speed in this case of the driven, which is N2. So how can we calculate the speed? All right, so in this case, yeah, they wasted a lot of time for us even giving this tension. They are not even important because we can use the ratio between the diameter and the speed in this case. Remember that the product of D1 and N1 is equal to the product of D2 and N2. So this can be used to calculate whatever that you want. In this case, we have to calculate N2. Remember, I asked you to calculate the speed of the rotational frequency, in this case of the driven. So that is N2. So you can substitute your values. That is D1 is 0.12 in meters, or you can use it in centimeters, but you have to convert this one to centimeters. You are supposed to use these in the same unit. So that's why you are supposed to convert to the basic unit of what? Meters. So in meters, that is 0.12. In this case, multiply by N1, which is our N1. The speed there is 20. Remember, it's in revs per second. So meaning to say N2, we are going to obtain it in revs per second, right? Which is equal to D2, which is 0.2. So that's 0.2 times N2, which is the one that we are supposed to calculate. So you can divide by 0.2 since we are multiplying in this case. So this will cancel. We remain with N2 in this case. So the speed of this part is going to give us, if you divide this part here, you're going to obtain 12 revs per second. All right, so that was the rotational frequency. The rotational frequency is simply indicating or simply represents what? The speed. All right, so that is how we're supposed to answer the question. Then 1.4, the power transmitted by a belt pulley. All right, let me try to push it this side so that we can work it properly here. All right, this is what we have, guys. This is what we have as part of our question. The power transmitted by a belt pulley with a diameter of 16 centimeters rotating at 760 revs per minute is 8 kilowatt. T1 as to T2, which is the ratio, is 3. And the allowable tension is 15 Newton per millimeter. 15 millimeter per millimeter per belt width. It is calculated per belt width. Calculate the width of the belt. All right, 6 marks for that. Okay, this one is very, very important type of a question. So let us take our information. We're talking about a belt pulley, which has got a diameter of 16 centimeters, the speed of 780, and the power of 8 kilowatt. Let us just take our information for now so that we can see how to answer this question. So remember, our diameter in this case is 16 centimeters, convert to meters, divide by 100. Remember, that's 0.16 meters. We are also given the speed there, remember, 780 revs per minute. We do not know what's going to happen. Let's just leave it like that. And the power, which is in kilowatts, which is 8 kilowatts in this case. That was the information. Then also we have got a ratio T1 as to T2, which is 3. Okay, T1 as to T2, which is 3. So how can we present this? If we are given T1 as to T2, which is 3 like this, it means it's 3 as to 1. That is what it means. So here we are given as 2. So meaning to say, if we are to write it as a fraction, we can write T1 over T2 is equal to T1, which is 3, T2, which is 1. So it means T1 S to T2 like this is going to be given as 3/1. That's why you see 3/1 is 3. So that's why they just wrote a 3, but there is a 1 which is there that you're supposed to take note on. And also we are given that the allowable tension in this case is given as 15 Newton per meter per meter belt. All right. Let us take this into consideration. Remember, it's taken per belt width. Is taken per belt width, the allowable tension. So where does it affect us in actual sense? Where does this part affect us? This part, guys, of the allowable tension, it affects us on T1. Remember, on the tight side, T1 is going to be equivalent to the allowable tension. In this case, we're going to have this as the allowable tension multiplied to the belt width, because it's given per belt. If you check, it's the allowable tension that we are given per belt width in this case, which is width of what? Of belt, or the belt width. So it's taken per. So meaning to say, in order for us to have the allowable tension, which is the exact tension, which is our T1, we are supposed to use the allowable tension per width of the belt times the width, because the moment you multiply by the width, per means over. It's like we've got a tension, we've got T1 over the width. The moment we multiply by the width like this, it will cancel. So in order for us to find T1, to remain with T1, we have to use the belt width in this case. So it's going to be the allowable tension times the belt width. Please be careful on this one, times the belt width, which is, this is taken per millimeter, and the belt width must be in millimeters also. So the belt must be in what? Millimeters. So what does it mean? Do we have the belt width? No. The belt width, we do not know it. So you can just maybe indicate with W or a small w, I don't know. So meaning to say, we are simply saying T1 is going to be the allowable tension that we are given here. Remember, the allowable tension is 15 Newton per millimeter. So this one is going to be 15 Newton per millimeter in this case. So it's per millimeter. That is why we are supposed to multiply with the millimeter, so that millimeter and millimeter cancels, you remain with the Newton. So meaning to say, this width that we are supposed to calculate, it must be in what? It must be in millimeters. So it's going to be 15 times the width, which is the belt width that we do not know. So we do not know this belt width. So this is going to be the formula to represent T1, which is supposed to be measured in newtons, because the per millimeter and millimeter, it will cancel. So meaning to say, T1 was actually supposed to be given as 15 W in Newton in this case, whereby the W is representing what? The belt width. The belt width, this W here represents the belt width, which is in millimeters. So this is our belt width in millimeters. Okay, so someone is asking, why are we even concentrating about this T1? Why can't we just answer the question direct? Okay, it's very, very important for you to just analyze this information and understand, what does that information alone mean? What does it mean? So that when you're answering the questions, it's going to be easier for you. Like in this case, remember, we have got, this is what you're going to ask yourself. I'm supposed to calculate T1. You see that analysis now, where it helps you now. I'm supposed to simply calculate T1 in this case. By calculating T1, I simply have to divide by 15 so that I find the W, which is what? The belt width. But where am I going to have the T1? So it means for you to obtain the value of T1, you are supposed to form equations, or an equation which consists of T1, and solve for that T1. Which equations that we know that consist of T1? All right. One, it is the ratio that we have here, because here we are given that T1 is equal to 3T2. This one is a ratio. T1 over T2 is 3/1. So it means from this ratio, T1, okay, let me write this so that I do not take you away. So we are going to calculate T1 in order in order to find the value, of W in this case, where W represents what? The width of the width of the belt. So to calculate T1, formulate equation or equations. We are supposed to formulate is either it's going to be a direct equation or they are going to be equations. I do not know, depending with the question, depending with the information. So let us formulate our equations to calculate T1. We said the first one is going to be taken from this T1 over T2 is 3 over 1. From T1s to T2 is 3. So it means T1 over T2 is equal to 3 over 1. So from that ratio, we are saying T1 over T2 is equal to 3 over 1. If we cross multiply, it means that T1, 1 times T1 is equal to 3 times T2, which is 3T2. So as we can see, yes, we have formed an equation for T1, but we can't solve this because we have got an unknown value again there. So let us just leave it like that. Let's find another formula, which consists of what? T1. The major part, the formula must have T1. The formula is supposed to have T1. Which formula can we think of? Let's think of the power, all right? From power, which is P. So remember that power is equivalent to the effective tension times velocity, whereby the effective tension is taken by T1 minus T2 times the velocity. There is a T1 there. So meaning to say we can form an equation since we are given what? The power in this case. We've got the power, but we do not have this V. So the question is, where are we going to obtain the value of V? Where are we going to obtain the value of V? Remember that V is equivalent to pi dn. If given this n in revs per minute, you are going to divide by 60 like this. So it's going to be pi dn over 60 in revs per second. In this case, to obtain V in meters per second. So we have, in this case, everything. So it's going to be pi, in this case, times the diameter. We have the diameter here. Remember our diameter in meters, 0.16. So we're going to have our diameter as 0.16 times n, the speed in revs per minute, which is 780. So that's 780 there. So we are going to obtain, okay, we're going to have 780 over 60 like this. So this is going to give us the velocity in meters per second, which is going to be 6.535 in meters per second. So obtaining the velocity doesn't mean that we have obtained the value of T1. No, it is simply going to help us now to substitute here so that we have a formula for T1. So we do not have T2. So it means we are going to, as we are seeing, we have formulated, this is the second equation now that we are supposed to formulate. So it means we are going to end up having simultaneous equations there. All right, let us substitute and see what was going to happen. P is the power, which is our power here, 8 kilowatts. So we've got 8 kilowatts. Remember, kilo means 1,000. So that's 8,000, or 8 times 10 to the exponent of 3. So we have got 8,000 is equivalent to T1 minus T2 in this case times the velocity, which is of 6.535, the velocity that we calculated here. So we are simply applying the value that we calculated. And as we can see where our equations are going here, we are simply supposed to find an expression or the equivalent of T1 over T2. So you can simply divide by 6.535 both sides. 6.535 both sides. All right, so this was going to cancel. And we remain with an expression that T1, in this case, we are going to divide. All right, even before we divide, guys, let us do it this way. Because what you're going to obtain in this case, or what you were going to have, I'm not saying at this stage it's not going to work, but the value that you're going to have is going to remain with the T1 and T2. So to avoid this, guys, let us do this at once so that we obtain another value here at once. So, okay, let me just do this way so that I do not confuse you guys. Okay, like this. Before we can just, yes, if we divide, it was fine. I'm not saying it's wrong, but we are going to have a lot of calculations encountered there. So since we have a relationship that we have already taken into consideration that T1 is equal to 3T2, let us just calculate T2, because instead of finding T1, yes, it's fine, but let us just substitute at once here, because T1 is what? 3T2. So in place of T1, you're going to substitute 3T2. So it's going to be like here, it's like a 1. So it's 3 minus, in fact, here it's a 1. So it's 3 minus 1, which is 2. So we are going to obtain something like this. 8,000 is equivalent to 2. 3 minus 1 is now a 2 here. 3 minus 1 is now 2T2. Remember, we say T1 is 3T2 like this, minus T2. So it will be 3 minus 1, which is 2, and times 6,3, okay, 5, 3, 5. Okay, so simply multiply this by 2 so that, because these are numbers, or simply divide by these numbers, you obtain T2 at once. You can simply divide by what? Since here you are multiplying by 2 and here you are multiplying by 6,5 at once. This is what I was simply saying, that you can find the value of what? T2 at once, all right? So this was going to be easier for us. This one and this one cancels. This one and this one cancels. We remain with what? T2. So meaning to say our T2 was going to be what? At the end, we divide these two. 8,000 divided by the product of these two numbers, you were going to obtain 612,089 in Newton. So it was so important for you to work out in an easier way than to be difficult on yourself. Here you can calculate the value of T2 direct by substituting what is equivalent to T1. So what's the advantage of doing this? Remember, our major focus, it is not to calculate T2, no. Our major focus is to calculate T1. So you could have substituted in terms of T1 direct, but it was going to be a fraction, which is fine. Guys, this solving part is in your hands. You play around the way that you're comfortable with. All right. So it means now we can calculate T1, because we said T1 is equal to what? 3T2 here. So that means T1 is going to be 3T2. So that's T1 is going to be 3 times T2 in this case, which is a 612,089 in Newton. So that's the value of T1, 1,836,267 in Newton. What was the purpose of calculating T1? Remember, the purpose is for us to obtain the width, because we are saying T1 is the allowable tension times the belt width. And we formulated an equation that I was explaining, that T1 is equal to 15 times W, which is the belt width. T1 is equal to 15 times the belt width. So if T1 is equal to 15 times the belt width, we are going to take this into consideration, that this T1 that we see here is 15W, because T1 is equivalent to 15 times the belt width. So that is, we are going to substitute in place of T1, we're going to substitute this. 15W is equal to 1836.267. Divide by 15 both sides. Divide by 15 here, we are going to have the belt width in this case. So if you were to divide these two, you are going to obtain 122,4178 and so on, which is going to be 8 in this case. 7, 8. 8 is going to change this into 8, which is in millimeters. Remember, we said this was taken per it was per millimeter, which is belt width times the belt width. So this belt width, like I said, it must be in what? Millimeters. So meaning to say, at the end, we are going to obtain our answer for the belt width in this case as what? as 122,418 millimeters. Guys, there are so many ways that you can work out this question, or that you can play around this question. There are so many ways, but just try to work it the way that you understand and the way that is easier for you. But you're supposed to obtain something of that nature for this question. All right, so let us not waste much time. Let us check the other part of the question here. All right, so there we are. Question number 2, it was on the moments part, and they were given. All right, let's check. Did we cover everything here? Yes. All right, so that was it. 16 marks. Question 2 on moments. Let's try to have it. Sorry for that, somewhere here. All right. So how are we going to attempt this question here? Give the difference between a concentrated load and a uniformly distributed load. 2 marks for that. Okay, so this I'm just going to explain from this part. Let us see here if possible. All right, so that's it. The concentrated load is simply the load acting on a point or point load and normally act vertically downward. That is a concentrated load. Remember, if you are talking about a concentrated load in this case, we are simply talk about those loads that will be facing down in this case. And so a load that will be acting downwards, and so it's acting down normally given at a point. Whereas a uniformly distributed load is a load that is spread evenly over the length of a beam or a part of a length of the beam. That is the difference that we have on a concentrated load to say is the load acting on a point or a point load and normally act vertically downwards. All right, so that's I think is direct. Let us check the other part, which was in this case to question 2.2. A uniform beam which is 10 meters long is a mass of 150 kilograms per meter, and it is horizontal. It is horizontal and rests on 2 supports. All right, so this we are supposed to sketch and indicate all the forces acting on the beam. All right, so let us try to have a sketch. Normally, this one is best for us to have it. So it's just best. Let's just have a line of this nature. Remember this here we're given it as uniformly distributed, like it's distributed throughout. Okay, let's just go back to the question and see what we are given here. They are saying, okay, there we are. They are saying here, sketch the diagram and indicate all forces, which is fine, but I want this statement here. A uniform beam is 10 meters long and there's a mass of 150 kilograms per meter along the 10 meters. Along these 10 meters, it is distributed throughout this one, distributed throughout along the 10 meters. So meaning to say, let's say this is where we are having our 10 meters. It is going to be distributed throughout. That is what we are given. It's distributed this one throughout. All right. For the rest of what? For the rest of the 10 meters, you are going to have this as a distributed load. That's what they are saying. Okay. So we've got 10 meters from the first point to the end point. We shall see that one at the end. Let's see. It's having 150 kilograms per meter. So if it is distributed for the 10 meters, we are going to multiply by 10 to obtain it as a point load. But before that, this is mass. So you're supposed to have the force acting from our gravitational force. In this case, we're going to apply the weight component in this case, which is our weight is given by mg. So we are going to calculate the weight, which is equivalent to the force in actual sense, which is supposed to be mg. But it is going to be the force per meter in this case, because this is mass per meter. So we're going to have the mass of 150 times the gravitational acceleration of 9.8, which was going to give us 1,470 Newton. But it's taken per meter since we used the mass as kilogram per meter. But this is taken now over the what? Over the 10 meters. We shall talk about that later on. All right. it is horizontal and rests on two supports, one 2 meters from the left end and the other 1 meter from the right end. All right, so we have got 2 meters from the left. This one, the first one, let's see, these are supports now. 2 meters from the left end. So this is our left ending here, our left end, it's at this side. So just 2 meters from there, we can just maybe here, remember a support is going up. So we are going to have our support here facing up. All right. That's 2 meters from the left end. So at the left end, we do not know what's going to happen. Maybe maybe there's a point load there or what. Let's just put the dotted lines to indicate our starting point. But what we just know so far is that the distance that we are given in this case is 2 meters. That's what we know. The difference here that we are given is 2 meters. It is 2 meters from the left, and it's given as a support, okay? Then also, the other one is 1 meter from the right end, from the right hand end. There's another one that is 1 meter from the right. This is our right, 1 meter from there, maybe somewhere here. So what we just know is that there's a support here, which is 1 meters from the right hand. At the right hand, so far, we do not know what's going to happen. Are we going to have a force there or what? But what we just know is that from this right hand to this point, there is a difference there of what? Of 1 meter this time. There's a difference of 1 meter. So this is a support, it's facing up. Then they are saying, in this case here, from it carries a concentrated loads. Then we have got the concentrated loads. On the distributed load, there are also concentrated loads that are considered, which are facing. Remember, the concentrated load are the ones that are facing downwards. And so we have got 450 Newton and 700 Newton. The first one is 1 meter and another one 4 meters from the left end of the beam. So meaning to say we have got 450, this one, which is 1 meter from the left end, 1 meter. So 1 meter, remember here, there's a difference of 2 meters. Yes, so 1 meter is going to be in between, but this one is a concentrated load supposed to be facing down. So we draw it from top in this case. So that is going to be our concentrated load like this, all right. So they are saying the difference that we are going to have in between is going to be of 1 meter from this point of the left hand side here, from the left hand side to this point, there is going to be a difference of 1 meter from the left. But remember, before we are told that the whole distance here is 2 meters. So it means also we subtract 2 minus 1, we are going to be left with 1 meter in between. So this is our point load of 470 Newton in this case. Is it 470 or 450? Sorry for that, 450. So this is 450 Newton like this. All right. Then another one, it's 704 meters from the left. 704 meters this time. So already we have covered from this point to this point is 2. So we're going to cover another 2, maybe somewhere here. That's where we have our 2 somewhere here. Okay, so do not mind my diagram because yeah, it's gonna be something else not accurately taken, but that is the idea there. So this will be 4 meters from the left end, meaning to say from this point to reach this point, from the left end to reach this point, there's a difference of 4 meters from there. So what does it mean? We can simply focus on this one that is remaining. If the whole of this distance is 4, what about this one remaining? So it's 4 minus 2, meaning to say we've got 2 meters in this case. So that was going to be the force, the concentrated load of 700 that is affecting at this point. So we are affected by 700 Newton there, okay? Let's move on, guys. Let's see. That's it, you're done. But remember of our distributed load before that we are given a distributed load of 1,704 Newton per meter. On the diagram here, guys, what you are just going to indicate, it's not important. You just indicate to say this is distributed. So you can just indicate it either here or wherever that you want. That we have got what? 1,470 Newton per meter. This one is representing the force that we are, the distributed load for everything. On our calculations, that's where now we are going to multiply by the distance in between to have it as a point load or as a concentrated part load. But for now, we are using just as a distributed load on the diagram. It's wrong for us to write it on the diagram as a concentrated at once. No, let us have it properly, this question. All right. So remember, we're given that the distance between every point here is 10 meters. That is the length of the beam. It's given as what? 10 meters. So what is going to be the remaining distance that is remaining here in between? What is going to be this distance here remaining? Let us see. There's a distance here that is remaining between these points. If we take note, there's a distance remaining there. So how are you going to calculate? We are going to subtract from 10. So it's going to be 10 minus these 2, minus this 2, minus this 1. So it's 10 minus 5, which is going to be 5. So it means in between there, we've got 5 meters. That is the distance between. All right. So you can even leave it like that. You can obtain all the marks in this case. All right. So that was to sketch on on 2.21. It was to sketch. Let's see the other part now where we are supposed to apply the force. There we are now given to calculate the reaction of the supports. All right, so for that here, 2.22, calculate the reaction of the supports, which is 6 marks for that. To calculate the reaction of the supports now, that's where we have to consider to say, all right, there is a distributed load that we are given. So 2.21, here we are done. On 2.22, we are going to use this diagram. On using this diagram, that's where we are supposed to ask ourselves now to say, all right, what about that one that we were given before that we did not consider to say, yes, it's a distributed load that we have here of 1,470 Newton per meter taken for the 10 meters. So we're going to multiply by the 10 meters. Remember, it's per meter, 1,470 Newton over a meter times a meter. It will cancel, you remain with the newtons only. So that's why we have to multiply by the distance that you are given. So 10 Newton, this one per meter times the distance of 10 meters simply means the meter and meter cancels. We've got 1,700 Newton represented now as a concentrated load. So that is how we are going to take it in between, but taken in between 5 meters because it's taken over the 10 meters. So you divide 10 by 2, which is going to be 5 meters. So let us just say somewhere here, 5 meters, maybe somewhere here in between. So here I'm going to use a different color because this is not part of our diagram here. This one is not part of our diagram. We are adjusting to the information so that we'll be able to calculate what we want. So now we are using it as a force, as a concentrated load of 14,700 Newton. Separated between what? Separated between the distance of 5 meters between this whole 10 meters. Remember, the whole of this line, it is 10 meters. So you divide by 2, meaning to say, as we are moving from this point here to this side, there is 5 meters there. So it's going to be 5 minus 2, which is mean there's 1 meter in between here. So in between these 2 points, there is 1 meter there. Remember, we are saying here we have covered 1 meter. Here we have covered 1 meter, but we are supposed to cover 5 meters up to the end. So it's going to be 5 minus 1. We remain with 4 meters. So here there is 4 meters that we are remaining with. Here there is 4 meters. Remember, we said the wall of this one is 5 meters, this one. The 5 meters is the wall from this point up to this point. That is where we have 5 meters. But from this point here, of 14,700 up to this point, it's now 4 meters plus this one. It gives us the whole of the 5. If we move on to this side from here to here, it's 1 meter, but the rest must be 5. So it's 1 plus this 4, which gives us a 5, which is true. And the wall of this line is 10 meters. So That's we can use this diagram now to calculate the value of the reaction. So on the naming part, it depends how you're gonna name your diagram. So you can maybe start this as your A. This force will be your, this one will be your B, your C, the 700 to be your D. Yes, you can write E for this one, but remember this was not even part of our diagram. It was just given as a normal, as a distributed load before. So yes, we can write it as E. Then you can move on to this one as F, then this one as G. At the naming part, it's up to you. All right. So meaning to say, according to this, our supports is going to be C, and this one is going to be at F. So let us start, or for calculating F, we can start with that. It's up to you. So taking moments about C in this case, taking moments about C. So what does it mean? Remember, if you take these moments about C, we are going to have a rotation of F going this side, which is going to be this way to C, which means you are considering it in the anti-clockwise. So you're gonna have the sum of the anti-clockwise moment equal to the sum of the clockwise moment. Which forces are going in the anti-clockwise? The F here is going this way, as F is going, it's moving this way. So F is moving in the anti-clockwise. All right, let's check with 450. 450 is on this side, and as it is moving this way back to C. So it's also in the anti-clockwise. So this one is also in the anti-clockwise. But if we check the 700 here and the 14,700, as they move back to C, they are moving this way, which is clockwise, and moving this way, which is clockwise. So in this case, we are going to add, that is the sum of the anti-clockwise, whatever that we have in the anti-clockwise together, and we combine to what we have in the clockwise. So in the anti-clockwise, remember, we said F, as it is going back to C, it's anti-clockwise. So it's F times the distance from F to C. What is the distance? There we've got 5 plus 1, which is 6, plus this 2, which is going to give us an 8 in this case. Right, that's a 7. Is that so? So the rest here, it's 5. Okay, sorry for that. Remember, we said the rest of this line here is a 5. This one, the whole of this line here, it's a 5 in between. So it's 5 plus 2 from here to here, 5 plus 2, which is 7. So it's going to be F times 7. We also have another anti-clockwise that I indicated here with an arrow, the 450. So we're going to add 450 times the distance back to C, which is 1 meter. Remember here, there's a distance of 1 meter. So that's it. We move on to the other one. The others that we are seeing here, they are in the clockwise. Which one? We talked about the 700 going this direction clockwise, the 14,700 going this, which is clockwise. So we're going to be left with 700 times 2. So this was going to be equal to 700 multiplied by 2 plus 14,700 times the distance back to this point. Remember, from here to here, it's 1 meter. Here, it's 1 meter from this point here. So if it is 1 meter, it's going to be 1 plus 2, which is going to be 3. So we are going to have this one multiplied to 3, okay? So that's it. We can have the value of F combined. F times 7, that is going to be 7F plus 450, which is equal to, combine this whole part here. You are going to obtain 45,000 in this case, 45,500. Transpose the 450 to this side, it becomes what? A negative in this case if we transpose. So that 7F is equal to, we are going to subtract 450 here. So if we subtract 450, we're going to obtain 45,050. 45,050. So you can divide by 7, since we have to calculate the value of what? Since we have to calculate the value of F. So this was to cancel. So our F is going to be given as what? If we simplify 45,050 divided by 7, 45,050 divided by 7 is going to be 6,435, 714 in Newton. All right, so you can even write it in kilonewton if you want. You can even write this in kilonewton, which is fine. But that is how we could have calculated the value of F, which is a support, the first support. All right, let's consider the second support here. So this is our F. Then for the second one, which is at the support here, we're gonna consider from F this time. All right, so this time we're gonna consider taking moments about F, not about the point. So here we're gonna remove this part here. All right, something like this. All right, so let's say we are to take moments about F in this case. How are we going to calculate, or how are we going to obtain the value of C? All right, so let's see what we're gonna have in here, taking moments about F. All right, considering F, now if we check C as it is moving to F, this is our C, moving back to F, this is a clockwise direction, as you can see, clockwise way. So it's gonna be clockwise. So I'm just gonna consider the sum of the clockwise moments being equal to the sum of the anti-clockwise moments. That is from C back to F, we've got a distance again of 7, here we've got 2, and from here to here we've got 5. All right, so which is fine. But let's check others also in the clockwise. Which other forces are moving in the clockwise to F? So if we check this one, the 14,700 is going this way to F, which is anti-clockwise. So here we've got an anti-clockwise, here we've got an anti-clockwise. At 450, we also have an anti-clockwise. So all these forces, they're in the anti-clockwise there. So let us start with the clockwise. C, back to 7, said it's clockwise, and C, we do not know the value of C, but what we know is the distance there, which is equal to the anti-clockwise. Let us start with the 14,700 back to F. So it's 14,700 times the force back to F. Yes, you can see from this point here back to F, there's a distance that we indicated here of 4 meters. From here to here, we said it's 4 meters. So we are going to take the distance there of 4 meters plus another anti-clockwise, which is of 700. So 700, now we consider the whole of this line up to F. Remember, in between here, the distance is 5 meters, the 4 and the 1, which gave us 5. So it's going to be 700 times 5 plus, we also have the last one, the 450 back to F. So this one, we are simply removing this one and this one only. So we are going to remain with, out of 10, we are going to remain with 8. Or you simply add from this point up to this point is 5. From this point up to this point is 2. We are now at 7. From this point to this point, we add the 1, which is now at what? At 8. So it was going to be 450 times the distance back to this point, which is 8. So that is how we are supposed to work out this question times 8. So as we can see, at this stage, we can be able to calculate the value of C, just like what we did on the value of A, in order for us, on the value of F there. So in order for us to calculate C, we're gonna combine everything. 7 times C, C times 7, which is C7 or 7C, is equal to combine everything. On the right-hand side, in this case, you're going to obtain 65,900. So that's 65,900. You can divide by 7. You can divide by 7. That's to obtain the value of C, which was going to be 9,414,286 in Newton, or you can write this in kilonewton. Then you can test your answers. But as I always say, the testing of answers is not a guarantee that your question is correct. No. If you worked one value wrong and you used that value to work another value, it is going to balance because of this equation concept to say there is something that you worked and there is something that you worked and there is another one that you worked. So what is important there is that work out separately. Okay, work out separately, understand your question, understand how the question is given. So that's how the questions are given, as I just hope you understand. So like I was saying, if you just test your values here and you see they correspond, that part alone is not to mean that you are correct. No, it does not mean that you are correct. So it can be out of a wrong answer that you obtained. You used the wrong answer to find another answer. So it balances because of the substitution technique that you are using. But let's continue to revise, guys, as much as you can. That can actually help in this case of this typical question. So remember, that was the information that we had taken from this question number 2, working with the beams, in this case, working on our moments. All right, so that was it, 12 marks for that. All right, question 3, which is now just revision. Define triangle of forces with aid of diagrams. We are not just supposed to, okay, just describe. No, we are supposed to use with the aid of what? Of diagrams. So that's question number 3 and 3.1. Triangle of what? Triangle of forces. All right, so what is the concept of our triangle of forces? Remember, on our triangle of forces, we have got a consideration whereby we have got 3 forces that are going to be in equilibrium in this case. Let's say we are given 3 forces that are in equilibrium, and we've got 1, 2, and 3 in this case, forces. All right, let's just say forces in equilibrium. All right, so given 3 forces in equilibrium, they can be represented in magnitude and direction by the sides of a triangle if they are taken in a sequence. So we're going to have this in the presentation of a triangle. All right, the first one, the 3, that is the 3 going down, the 1 going this side here, this is our 1, and we join this with the 2 like this. So that is like I was saying, to say we are going to say they can be represented in magnitude and direction by the sides of what? Of a triangle, and it's actually a closed triangle in this case. If they are taken in sequence, so the sequence is this one that we are seeing, 1 from this 1 and 3 and the 2 in this case. So we're gonna have this way. All right, remember 1 is going this way, 3 is going down, 3 is going down like this, and 2 is slanted. So you're just gonna have something that is slanted like this, a slanted force like this, okay, going this side. So that is our 1 on the horizontal, our 3 on the vertical, and this one our 2. Okay, so let us have this in words. So we are saying if 3 forces, all right, if 3 forces, if 3 forces acting on a point, acting on a point, like I explained before, in equilibrium, in equilibrium, all right. So these ones considered to be in equilibrium, then they can be represented in magnitude as this part here. They can be represented. They can be represented in magnitude. All right, in magnitude and direction in this case. All right, in direction by the sides, or by just sides of what? A triangle, or a triangle. All right, so that is the condition that you are going to have there. But it must be if they are taken in sequence now, all right? If they are taken in sequence, if they are taken in sequence. that is how we could have explained in form of diagrams. Then we explain what is happening. Okay, which is a nice part, just to frustrate you further to not understand there. That's what they try to do. Calculate the magnitude of the resultant forces acting on the object at equilibrium. So this is what we have. So this was just a vertical horizontal line. This one is a continuation of a horizontal. Don't mind this diagram that way. Then this is a vertical one. So remember, I said all forces should be taken from the point going out in this case, not to be taken into. It must be going out. So as you can see, this force is going out, is going into. So you're just going to extend this on top here as it is vertically up. So we are going to have this on top here, the 55 Newton, we are going to have it on top like this. So at the end, if we were to consider this just like, let us just save it as a sketch. All right, 3.2, we had something in the horizontal, then we now have that one that we have taken from the one that was in the vertical, this one, okay, from this one in the vertical. We are no longer considering this here because we have taken it up. So you're going to use this 55 on top. Don't take the forces that are facing the point, take them as they are going out. So you're going to take it as, so that you do not confuse in terms of signs, this and that, because there are so many adjustments that you are supposed to take. So the 55 Newton is this one that was down here. The rest, they are taken, as you can see, this one is going out, this one is going out, this one is going out. So all these, they are fine. So here we've got 50 and 45. All right, so there is a 50 Newton here along the horizontal. Here there is a 50 Newton, and in between there at an angle of 50 degrees there is a 45 Newton. This one is there, is just given. There's nothing, no adjustments that you are taking. This actually, if you check, this question paper was one of the nice questions. You can't say it was easier, but it was one of the nice question papers. Maybe it's because we have revised a lot of things, so it's just a repetition to us. All right, this one was 60 Newton also. Oh, sorry, 60 degrees. Sorry for that. 60 Newton here. The angle was not 60 degrees. It was 40. Let's check. It was 40 there. Let's check if I'm still remembering this. Yeah, the angle there, it's 40 degrees. All right. So here there's an angle of 40 degrees here. All right. So that was the only part that we had to shift is this one that we had just wrote on top. Remember, from our forces, we talked about this part. So the question was for us to have what? The resultant in this case. Calculate the magnitude of the resultant. All right. So the magnitude of the resultant, we are simply going to need the horizontal components in this case, and the components, that is the horizontal and the vertical components in this case. All right. So remember, the vertical component, we are working with the sine of theta from the concept of our sine theta opposite over adjusted, or opposite over hypotenuse, in this case, opposite over hypotenuse. So we are referring to the vertical, the opposite there. So we could apply the ratio of sine. If you just take note of this, guys, vertical is sine, horizontal is cos, okay? So let us have this, the vertical. 50 can never be vertical because this one is on the east line. It's an exact horizontal line. So this cannot, unless if you want to use it as 50 sine of 0, which is fine, 50 sine of 0, because here we are at 0 degrees, but there is no need for us to have it like that. Know that this one is not the total land, okay? Or you can just write it as 50 sine what? 50 sine 0 degrees, okay? Which is okay. Okay, let's move on to the 45. It's on top. Remember, everything that is above the horizontal line, everything above becomes positive, everything below negative as compared to the horizontal line. So all these forces, they are above the horizontal line. So they'll be all taken as positive, meaning to say we've got 45 sine of 50. So this is going to be plus, sorry for that, plus 45 sine of the angle in between, which is 50 degrees. Then this one is a straight vertical. If you want to use the angle, therefore you're going to use the angle of 90 degrees, but that one is a straight vertical. Just write it as 55, or it's a 55 sine of 90 degrees. If you want, you can write it as 55 sine 90, but this part simply is not important. All right, then here it's also on top for 60 Newton sine of the angle between. So it's 60 sine of the angle between, which is 40 degrees. That is what we could have written this as. But as you can see, this first part, it was not necessary to write. This second part, this one was not necessary for us to write. We just were supposed to write 55. But just for us all to understand what is happening from our diagram, then combine everything on your calculator. You are going to obtain our vertical component. In this case was going to be 128,039. All right, that is 0.39 Newton in this case. All right, so being positive on the vertical, being positive, it means we are going up to the north. Negative, we are going down to the south. So meaning to say this is going to the north. All right, that is the direction here. We are referring to the north. And let's consider our horizontal components. So horizontal component, they use the cosine of theta. So which is going to be also for the horizontal, it's taken according to the vertical. You compare them according to the vertical. To the right side of the vertical, it's positive. To the left side of the vertical line, as we are concentrating on the horizontal, but being on the left side, they are negative, meaning to say you're talking about being to the west and being to the west and being to the east, being positive. All right. So that is it. Let's consider. So according to this is our vertical line, the one that is separating to say our angles are positive or negative. So this side is going to be positive. This side is going to be negative. All right. So here, this one is a straight horizontal, guys. 50 cos 0 if you want, but that one, as you can see, it's a straight horizontal. So this is going to be 50 plus, we also have 45 back to the ground. So it's 45 cos 50 degrees, the angle that is between. So 45 cos of 50 degrees in this case. We can't have this as a vertical, as a horizontal, guys. 55, look, a straight vertical. So just leave it. Then let's move on to 60. Going to the ground is going to be 60 cos 40, but being on the negative side because it's on the left side of the vertical line, so it becomes a negative. So it's minus 60 cos 40. So this is going to be minus 60 cos of 40 degrees. So combine everything, you're going to obtain the horizontal component, in this case of 32,963, 32,963 in Newton in this case. And being positive, it means we are going where? To the east. Being positive, it means we are on the right side, that is to the east in this case. So this was being, or is going to be referred to the east. All right. So that is how we play with this typical question. This is actually going to the east. And how do you find now the resultant? The resultant, we are simply going to consider being horizontal and vertical. We take from our formula. So in this case, since the direction is not needed, it means our diagram is not even important. In this case, we're just going to consider the horizontal and the vertical components. Remember, to calculate the resultant, our formula is supposed to be taken. Let me write it here. Our formula from our Pythagoras states that R is going to be the square root of the horizontal component squared plus the vertical component squared. So you're going to consider the square root of the horizontal component, which is 32,963 squared plus the vertical component squared, which is 128,039 squared. We are taking what? The resultant in this case now. So this is going to give us the resultant of everything. And that was going to be 132,214 Newton in this case. We are now having the resultant of what? Of everything. On a consideration that you are supposed to be working with the angle in this case, you are supposed to indicate or work with the diagram now. So how are you? You have to consider to say this is to the north, this is to the east. So we are going to have our graph diagram in form of this Okay, let us just say we've got something of this. We have got to the east, which is the horizontal, and horizontal to the north. So which quadrant are we considering with east and north? This is the first quadrant. So we're going to have our triangle like this in the first quadrant, whereby the horizontal is positive to the east and the vertical is going up to the north. So this is our east side, which is the horizontal of 32,963. The vertical component, which is going up, which is 128,039. This is your resultant. So the theta, which is the direction, is the angle in between here, which is from the east going to the north. From the east side going to the north. So how do you calculate the theta now? Theta is direction. That one is now direction, but the magnitude we are fine. I'm just saying if we were to calculate the direction. So according to the opposite and adjacent, you see the favorite ratio, the best ratio is going to be what? Of tan. So where theta is simply arctan of the vertical component over the horizontal component. Vertical component over horizontal component. So theta was going to be arctan of the vertical component 128,039 over the horizontal component of 32,963. All right, so this was going to give us the direction now, which is our theta, and that was going to give us something like 75,563 degrees. Like I said, from the east to the north, direction from the east going to the north. So it's going to be east 75,563 degrees to the north. So that is when you are dealing with the direction now. But the first one, it was just the magnitude as it is. All right, so be careful on that part. So let's see the other part. Then on the other part, we are given now study the fig below and answer the questions. All right, so this is the diagram that we are given. All right, so let us see on the forces that we're given. We've got 60 kilonewton, 40 kilonewton here, 45, and the L in this case. Calculate the value of L. So here we are simply applying from our forces. Remember, the upward forces will be equal to the downward forces in terms of forces. So you can simply refer to the sum of the upward forces being equal to the sum of the downward forces. In this case, the upward forces, you've got L in this case plus 45 here. It must be equal to the downward forces, this one that are facing down, which is 60 and 40. So you're gonna have 60 plus 40 there, which is 100. All right, so L plus 45 is going to be 60 plus this, which is 100. So transpose the 45 to this side is going to be 55. Okay, so this is going to be 55 in this case. And also the units, consider the ones that you have here. So the units there is supposed to be in what? In kilonewton. So that is how we're supposed to calculate the value of L. So here we have got 55 kilonewton. All right, 2 marks for that. Calculate the magnitude and also the nature of this part of WR. WR, this side affected by 30 degrees. Remember, guys, I said in order for us to have this WR, we are simply considering the sum of the upward forces there and the downward forces again. But this time considering at RW in this case, there is an angle that is affecting of what? 30 degrees. So our upward forces in this case is going to be given as L. This is our upward force. So 55 is going to be the downward force, which is RW, sine of what? Of 30 degrees, since we are having an angle. So to find RW, simply divide by sine 30 this side. You divide by sine 30 this side. All right, so this was going to cancel, meaning to say we are going to obtain RW in this case. All right, so if we divide 55, divide by sine 30, this is going to be 110 kilonewton in this case. All right, then on the magnitude of PW, there's nothing there they are asking there, guys. PW is simply on the left, on the right-hand side. In this case, we are now considering the forces on the right and the forces on the left. So meaning to say from the right-hand side, we are considering PW in this case. So that, all right. And also RW, this one is going to be a strat, remember? So that's a strat here. And if we consider this PW, it's going to be horizontal. So you're going to have PW on the horizontal. Then consider it to RW to be on the left side. So it's going to be RW cos of 30 because this is on the left side. So the right-hand side must be equal to the left-hand side, but this must be cos of theta, which is cos of 30 degrees. So we calculated RW before, so meaning to say our PW is going to be RW that we calculated here of 110 times the cos of 30 degrees in this case. So that was going to give us the value of PW. All right, so PW is going to be 95,263 kilonewton in this case, and this representing what? A tie. So if you are, guys, on these roof trusses, if you are having challenges, guys, I don't know now how. This question, it has got 4 marks mostly. If it has got a lot of questions, it's going to be like this, whereby you've got 2 marks to calculate the value of the unknown force, and the 4 marks for you to calculate those and to name. And 6 marks for that. We can't be struggling like the whole of the trimester on this part. If you are not understanding how to take this, just know this concept that I'm indicating here. You are considering the first one, RW, on the upward force from L, then PW on the right side, and RW on the left side, but affected by angle of 30. So you're going to use the forces to the right, which is PW, the forces to the left, which is RW, cos 30. That is, even if it is here on this side, is the same scenario that we are having, whether it's on this point, it's the same layout like this one. So I don't know, because guys, we might work or waste much of time on something that has got fewer marks at the end in exam, and taking us a lot of time in presentation for you to actually understand where it was actually taken from, and that one is gonna be a lot for you to understand that. But that is the simpler part that you can take, knowing from our simpler formula. And forces to the left and those forces to the right, they're equal. Forces up and forces down, they're equal. If you can have that, it's going to be much easier. It's going to be much easier. 4.1, we're given, give 3 advantages of friction in this case. All right, so it's got some of the advantages here that you're going to consider. Friction prevents slip between 2 contact surfaces. We also have, it removes the material, transmit movement by means of belts, brings the movement to a standstill. So these are some of the advantages that we can consider in this case. Then we are given on question 4.2, the figure below shows the board R, which is set to rest under the influence of a spring balance P with the mass of Q. So we've got the mass of Q here. The mass Q is attached to the body by means of an elastic rope that passes over the frictionless pulley at M. The component of weight of the body parallel to the plane is 50 Newton in this case. All right, we are given the component of the body parallel to the plane, which is what, 50 Newton. Remember, parallel to the plane, we are simply going this direction here. That's where we are going to have our F parallel, also with our frictional force. In terms of our presentation here, remember, we are going to take this being perpendicular like this at 90 degrees. This is the perpendicular component. Then this is the parallel component like this, just like this, parallel to the plane. All right. So this is the perpendicular component, and we've got something of this nature, whereby here we've got the 60 degrees, which is the same as the 60 degrees here. So this is the parallel component to the plane, just like this part here that I indicated. So they gave us the parallel component of what? Of 50 Newton in this case. We are given 50 Newton. And the frictional force, which is also the frictional force goes the same direction. So you can also indicate, or let me just indicate the frictional force this side, so that we, because of the space here, the frictional force is given as what? 15 Newton. But where the frictional force is going is the same direction as our parallel force in this case, which is this one that I indicated here. All right. So the question is, let's see, calculate the following: the reading of the pulley scale P. We need the reading of the pulley scale P here, the reading at P. What is going to be the reading in terms of what? In terms of the force. We need the force that is going to be affecting there. How are we going to do this? That is the question now. How is this possible? All right. For us to have the reading at P, we simply need the value of the force that is affecting. So let's say the tension in actual sense. All right. So having the tension there at P, we are simply saying, I want you to see what is happening here. If we are to check this, it's not in much question. Let's put it this way. If we are to consider what is happening here, is we are taking this object, the object that is of 15 kilograms in this case. It's going to be a weight there. We are going to be considering a weight. This weight affecting, to say, if we are saying this will be going down, as we are trying to take it up, it's being influenced or is being taken by which forces that are going to affect the tension at the block of P here. There's going to be a tension or a force there. The parallel force and the friction of these are the ones that are in act. These are the ones that are in act, that are acting on this board. So meaning to say here, we are going to need the weight of this object, weight, which is mass times gravitational acceleration, the mass of 15 times 9,8 gravitational acceleration from our information sheet, which is 147 Newton. So what I'm simply saying, if we are to combine this, the 147, which is the one that is supposed to be affected, 147 Newton, it must be equal to the forces which are taking it up. Which forces are taking this force up? Those will be going down. So let us wrap it this way to say the 157 is the force that is going up. So we're going to consider to the forces which are going down, which are affecting these forces. They will be taken in the other direction down, which is the tension that is going to affect at P. So you need the value, the tension there at P, plus the frictional force, which is going this direction as the parallel force. So the frictional force, parallel force, and this one at P, they'll be going the same direction. So we're going to add all these ones because they are the ones which are affecting this to be moving this direction. All right. So there we can find the value of P. That was the consideration there. So 147 is equal to, combine this, you're going to obtain 65 plus P, whereby P represents the tension at this point. So you can even use it as T. All right. So transpose this to this side. 147 minus 65, which is 82 in this case, is equal to P. So like I said, T is the same as our, like here I'm just using P, but it's the tension. So meaning to say, we are simply talking about a tension here, a reading of 82 Newton at the end. That is the reading that you're going to have there. Then the weight of the body in this case, what is going to be the weight of the body? All right. The weight of the body is not taken from here. The weight of the body is the one that we are having here, or you're going to consider as R, which is the same as what is happening at P. Here is the same thing here. We are considering the same thing. So the weight of the body now we can consider, all right, since we have got the parallel component here, we do not have the horizontal, we have got the parallel component. In the parallel component, we have got a W there representing what? The weight. Not here, guys, not here. This is the object guys, let us take our information. All right. The figure shows a body shows a body R in this case under the influence of a spring balance P. So which means what is taken measured at R is measured at P with the spring balance. The spring is just for measurement. So when I would consider in the body there, we are supposed to be focusing on R. So that's why we are supposed to focus on this, not the object, this one. No, there we calculated, it's fine. We need here for this body. So we're going to focus with what? The parallel component, because we know that from our parallel component, what is the formula? From our parallel component, this is P. We know that this is the weight times the sine of theta. And we need this weight. So it's going to be the parallel component over the sine of theta. So our weight is going to be the parallel component, which is given as what? 50 Newton. Then the angle there is 60 degrees. So it's 50 divide by sine the angle theta 60 degrees in this case. All right, that's it. We are going to have the weight of the body, not of the object that of that other part of the object there. No. So this is going to be 57,735 in Newton in this case. All right. So that was going to be the weight in this case. That's how you answer this type of a question. Don't be afraid of the diagram in exam. Just look at the diagram, you panic. No, the diagram does not mean anything. Understand the meaning of, understand what you're given from the diagram, not to be frightened by the diagram. All right. Question number 4, a horizontal pulling force of 8 Newton is sufficient to move a block with a mass of 3 kgs. So we are given a pulling force, which is our frictional force in this case, of 8 Newton, sufficient to move the block with a mass. We've got a mass here of 8 kilograms on the horizontal. The frictional coefficient between the block and the horizontal plane is, so we are given the frictional component of 0.36. Calculate the following 4.31, the perpendicular weight, which is the weight of the block in this case. What will be the perpendicular weight? Remember, from the coefficient of friction, guys, what is the definition? All right, that's 4.31. The definition of the coefficient of friction. How do you take this? The coefficient of friction is simply from the frictional force over the what? The perpendicular force, which is taken from our normal reaction in this case. So that's it. We can use that formula because here we need the perpendicular force, and we have got the coefficient of friction here of 0.36, and we have got the frictional force there of 8 over the perpendicular component or the normal reaction. So cross multiply, you're gonna have 0.36 times the perpendicular force is equal to, this is same as 1 times 8, which is 8. So you can divide by 0.36, divide by 0.36, so that we obtain the value of what? Of the perpendicular force in this case. So the perpendicular is 8 divided by 0.36. So if we divide 8 and 0.36, we are going to obtain 22,222 and like that Newton. All right, that was the question. Then now calculate the angle of friction. How do you calculate the angle of friction? From the coefficient of friction. All right, remember, from the coefficient of friction, it follows that tan theta is equivalent to what? The coefficient of friction. Tan of theta is equivalent to the coefficient of friction. Since we have to calculate theta, it means the tan of theta is equal to the coefficient of friction, which is the coefficient of friction in this case is 0.36. So this is equivalent to 0.36. So to find theta, theta is going to be arctan of this value, which is 0.36. So from your calculator, you are simply going to use your calculator, shift tan, that is arctan, this tan, shift tan, you press the value 0.36, you are going to obtain 19,7990 degrees, okay, which approximates to 20 degrees. If you want there, you can just write just 20, but as it's supposed to be 19.7992, 3 decimal places. That was the question. That was the idea of our question, just like that. So as I'm saying, guys, you ought to revise and revise as much questions as you can. 14 marks for that. That was the whole part we were being asked in this case. Let us check question number 5. Question number 5, which is on the heat, and this one is direct again. Okay, no problem. Let's see. Question 5.1, we are given in this case the amount of heat energy absorbed or given off by a substance depend on 3 factors. Name these 3 factors. Okay, we are talking about the heat that is being taken off or taken in, as long as you're talking about heat. Remember that the heat transferred is equal to M, the mass times the specific heat capacity times the change in temperature. So then we are simply referring to the specific heat capacity in this case. So meaning to say these are the factors: the mass, the specific heat capacity, and the change in temperature. All right, so you can just list here as we've got the mass of the object. All right, we've got the mass of the object in this case. We also have the specific heat capacity, which talks about the type of part that is it water or what, oil, or so that is what we are talking about there. So we've got the specific heat capacity. In this case. We also have the change in temperature, which can be an increase, or if you are cooling down, it's going to be a decrease. So here we just talk about the change in temperature in this case. All right, so we've got the change in temperature. All right, so these are the 3 factors that were needed on our question 5.2. We are given water has got a mass of 0.4 ton, is heated from 27 degrees Celsius to 97 by coal with a heat capacity of, which is the heat value, the specific heat capacity of water, like we were talking about, say it must have a certain heat capacity. All right, so let's consider our information here. We've got the information that we are given about the water, and we've got also the information that we are given about the coal in this case. All right, so for the water, it was heated from, it has a mass of 0.4 ton from 27 to 97, that is the temperature. All right, so we've got the mass given of water of 0.4 ton. Remember, a ton has got 1,000 kilograms, so you're just going to multiply by what? By 1,000 in this case. Since a ton has got 1,000 kilograms, to convert to kilograms, you multiply by 1,000. So that was going to give us 400 kilograms. Remember the temperature, the initial temperature there being 27 degrees Celsius, and the final temperature for the water being 97 degrees Celsius in this case. And also for the coal, we are given that it is being heated from 27, which was our T1 and T2 from what I wrote there, by coal, with a heat capacity, which is the heat value per kilogram, in this case, 30 megajoules per kilogram. All right, so we have got the heat value here of 30 megajoules per kilogram in this case. And also the specific heat capacity of water, 4,187 kilojoules. Take note there, per kg degrees Celsius in this case. All right, so let us take the specific heat capacity of water, which is our C in this case, or you can just write it as specific heat capacity in this case like this of water, which was 4,187, which is in kilojoule per kg degrees Celsius like this. All right, meaning to say wherever we use this specific heat capacity, we must have our temperature in degrees Celsius. That is what it means there. All right, and also kilojoule, that's times 10 to the exponent of 3, because we must have joule per, not kilojoules. All right, so the first question was to calculate the rise in water, the rise in temperature of the water in Kelvin. So the K there is for the Kelvin. Remember, the rise of temperature here is given in degrees Celsius from 27 to 97, but they need the answer in Kelvin. So as we know that the rise in temperature is simply indicates the change in temperature. It increased, as we can see, from 27 up to 97. There's an increase there, there's a rise. So that's why they're asking this question as the rise in temperature, because there's an increase which happened there. So the change in temperature is simply T2 minus T1. but we must have this in Kelvin. Add 273. We are going to have this in Kelvin, which is going to be 370 Kelvin. Add 273 also here. You are going to have this in Kelvin, which is going to be 300 Kelvin in this case. All right. So we have got our values in Kelvin now. So you can just substitute T2, which is 370 Kelvin, minus T1, which is 300 Kelvin. So this was going to give us 70 Kelvin. In exam, if you have mistaken, you can just use your calculator, subtract these temperatures in degrees Celsius. Then at the end, write Kelvin, because the answer is the same, because you are adding 273. At the end, you are going to subtract it. So you are going to obtain the same thing, but you are supposed to have your values in Kelvin as we are given there. All right, so that was it. First part of the question. The second part, they need us to calculate the quantity of heat required. So the quantity of heat here, in order for us to have the heat, we are going to consider the two that we have, the one that was heated and the one that is heating, the water and the coal. So the coal is the one that is heating, but here, in order for us to have the heat, which is E, we must have the mass, because it's mass times what? The heat value. So we do not have this mass. So meaning to say here, we are bound not to find the heat. Let's consider when we are referring to the water, the heat is going to be taken from the formula. Remember, the heat is going to be Q is equal to mass times the specific heat capacity times the change in temperature in this case. All right. So we can consider this. We've got the mass, the specific heat capacity, the change in temperature. So here we can use from the water. In this case, we are going to calculate from what? From the water. All right. So that means we are going to use the mass of water, which is Q is equal to the mass of water. This is not mass of fuel, no, of fuel, of this fuel, which is coal. No, 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 no. This one is the mass of water, remember. So I've got 400 kilograms. The mass of water, 400 kilograms times the specific heat capacity of water, 4,187 times 10 to the exponent of 3 in kilojoules. All right. But take note, it's per kg degrees Celsius. So means that this must be, the temperature must be in degrees Celsius this time. So the change in temperature, which indicates T2 minus T1, we are going to work it in what? In degrees Celsius. 97 minus 27. All right. T2, remember it's 97. So we are going to have in degrees Celsius 97 minus 27. So even if you have to say, you're going to see that you're going to obtain the same 7, but just because of calculations, we are supposed to use what? Degrees Celsius there. All right. So multiply everything in this case, combine everything, you're going to obtain 1,1,7,2,3,6,0,0 like this, which is in joules, remember, in the energy. So you can convert this value to kilojoules or megajoules, but as you can see, we've got 3 zeros, 6 there, values that we have. So you can convert to megajoules, divide by 1,000. That is going to be 117,236 in megajoules. All right, so that is it. We are going to have this in what? In megajoules. Or we can have it in kilojoules, which is going to be a bigger value. So it's better for you to work with a smaller value here. So that's 117,236 megajoules. That is the heat transferred, or the heat that is required. Then the quantity of coal, this is not heat of coal. What are they saying here? They need the quantity that is the coal that we have in this case, the coal, the mass, the amount of coal that we have, which is the mass. So here we are going to, remember I said we could have used this formula, but the only part that was shorting was the mass in this case, which is the one that we are supposed to calculate, which is the quantity of what? The quantity of coal. So now that we have this heat energy, because remember that E is equivalent to this Q is the heat, this one. We're talking about the heat energy there, the heat that is being transferred, which is the same as the heat that we have here, the same as the Q that we have here. So since these two values are the same, we are just going to take it from that part. So this is 5.22. So like I said, we are going to take it to the concept that E is the same as our Q. Heat transferred is same as the heat that is lost. So the heat that is for the coal and the one for the water, they will be equal. So meaning to say, since E is equal to the mass times the heat value, we can divide by the heat value so that we find the mass. So divide by the heat value here, by the heat value here. So this will cancel. We are remaining now with the mass of what? Coal in this case, which is the quantity of coal. So the question is asking for the quantity of coal. So meaning you say the mass is going to be given as the energy over the heat value, of which the energy that we are talking about here is the same as Q, which is our energy. We are going to take it in megajoules, as it is 117 point this in megajoules, because our heat value is in megajoules. So remember that was 117,236. And we have our heat value in megajoules per kilogram. So that's 30. We are going to divide by 30 there, which is going to give us the mass in kilograms. That was going to be 3,907,866 and so on, which is 908 in kilograms. All right. So that is how we're supposed to attempt the mass in this case, which is the quantity of coal that is required. This is not the heat that is required. This is the mass that is required. All right. Then on question number 5.3, all right, this question here, it was just an application of our steam table here. We are given that the boiler, a steam boiler is boiler developed steam under a pressure of 1,650 kilopascal. So we're given a pressure of 1,650 kilopascal, and wet steam is formed with a dryness fraction. Remember, the dryness fraction is X, which is 0.87. The wet steam is now directed to the superheater. So this is the wet steam, the information about the wet steam in this case. This steam is now directed to the what? To the superheater, where it is dried. And the superheated temperature there is 150. So we are now talking about the superheater in this case. The superheater. In the superheater, we are given the temperature there of the superheater, which is 150 degrees Celsius. And the specific heat capacity of steam in this case at superheater is 2.5 kilojoule per watt per kg degree Celsius. All right. So this is about the superheater. The question here is to calculate the enthalpy of 2 kg steam. The enthalpy of 2 kg steam of what? Of the following. The wet steam. All right. Remember H wet in this case, 5.31. Remember H wet is taken from HF plus XHFG, which is of evaporation of water, then end up of evaporation, and X being our dryness fraction, whereby these are taken from the pressure that we are given at 1,650 kilopascal. What is the value of HF there? So meaning to say here, we're going to need our steam table. Let us check if I have it here so that we can consider our steam table. All right, so versus pressure. Under pressure, we are going to need the value of HF and the value of HFG as needed on that formula. So under 1,650, under 1,650 under pressure, we check here, under our pressure at 1,650 here, this is where we are going to take our values under this part here of 1,650. So we are going to take HF there, go down with your HF. This is kilojoule per kg, HF and HFG in this column that is here and this column here. So we are going to have 865 for HF and 1,927 for HFG. All right, so these are the values that you're going to obtain in kilojoule per kg. All right, so we obtained our HF. Let us just substitute here since I showed you the value of HF. So H wet is going to be HF. Remember, we said our value there is 865. So it's 865 plus x, which is the dryness fraction of 0.87 times HFG for the evaporation. Remember, HFG there was 19,000, 1,927. All right, that's it. We are going to obtain H weight. And these values were given kilojoule per kg, kilojoule per kg. So our H weight in this case is going to give us 25,000, 2,541 actually, 49. The answer being in kilojoule per kg. So we are now given for the mass of 2 kg steam, what is going to be our H weight if we are considering a 2 kg steam. So we are going to multiply this by 2 kg. So the moment you multiply by 2 kg, that is the kg, and the kg is no longer there. No matter how you want to present these answers, but the kilojoule and the kilojoule, the kg and the kg, they will cancel. So you're just going to multiply 2 times the whole of this value, which is going to give us 5,082. So this is 5,082.98 in kilojoules in this case. Per kg, and the kg, they cancelled when we multiplied. So our answer can not be given in kilojoule per kg. That must be a correction to be made. It's not supposed to be like that. All right. Then the enthalpy of dry steam, which is Hg in this case. All right. Hg is just taken from our steam table again. At the same pressure of 1,650. If you check there, there's a value for Hg there. Let me show you here for Hg. If you check on top here, we have got Hg, which is next to HFG, or you add, since Hg is equal to Hf plus HFG, so you can add the values that we obtained before, or you can take it direct as it is. It is the same answer that you get. All right. So this is our HFG here, which is 2,792. So as you can see, this one does not need a formula. We are just taking it direct. All right, so let us have it here. Remember our value, guys, that we got there. We said our value for Hg. So this is 5.32. All right, 5.32. Our Hg, we said it's 2,792 kilojoule per watt per kilogram. But they are saying for a 2 kg, so we are going to multiply by the mass, in this case, of 2 kilograms. That was going to give us the value of Hg, which is 5584 now in kilojoules. Since we have multiplied by the what? By the mass in kilogram. This will cancel. All right, so meaning to say this information was actually useless. We do not have any person that considered this part of a superheater. They're just giving information to confuse you of a superheater. Why? I do not know. So, but that is what we're given. All right, question number 6, we are given hydraulics part, define fluidity in this case. Remember, fluidity is just taken from a concept of a fluid or a gas, which has no form actually, but it can take the form of the container where it is taken into, or it is taking the shape or the format of a what, of the vessel which is the container which it is captured in. So we can simply say it is a fluid. Okay, let us just have this as is a fluid or a gas, in this case, which has no form, but is going to take the form of the vessel, of the vessel. In this case, our vessel is the container, all right, in which it is captured, all right, in which it is captured, all right, in which there it is, all right. Sorry for that. Let me just remove 1 or 2 of this part here so that it cannot affect our part here. Sorry for that. In which it is, all right, it is captured, just like that. Okay, sorry for that. In which it is what? captured, or the container, or you can just have it as a container, something like that. All right. Question 6.2, we are now given the ram of a hydraulic press, in this case, can exert a force of. So remember the concept of a hydraulic press, and they're given the efficiency at 100%, meaning to say there is no effect. If it is at 100%, that it means the part or anything that uses efficiency on your calculation, it's good as just using a 1. There is no effect of that. So don't consider it if it is at 100%. So 6.2, we are given, in this case, we've got the ram, and we also have the plunger in this case. So on the ram, we are given the force that is being exerted on the ram. Just going to use the capital letter, which is 20 kilonewton. And the force of 0.6 is exerted on the plunger. So the plunger, I'm just going to use small letter F, 0.6 kilonewton. If the diameter of the plunger is 100 millimeters, okay, this is the plunger, the diameter there is 100 millimeters, divided by 1,000 milli, that's times 10 to the exponent of -3, which is 0.1 meters. And the efficiency is 100%, so this one does not affect us. Calculate the diameter of the ram in this case. Oh, okay, how can we calculate the diameter of the ram? Remember, we can connect these two, the force and the diameter in this case. Remember your formulas that, so it's gonna be 6.21. Remember, the force on the ram over the diameter squared of the ram is equal to the force on the plunger over the diameter squared of the plunger. So this is our ram, and this is our plunger in this case. So the question is calculate the diameter. We want to find this. So we can simply make the diameter the subject of the formula if we want, or we can just substitute our values in this case, which is F, 20 kilonewton. This is in kilonewton. This is also in kilonewton. So there's no need for us to change or to multiply by 10 to the exponent of 3. So we've got 20 over d squared is equal to F on the plunger, the force there, 0.6 over the diameter of the plunger squared, which is 0.1 squared. So that is how we're supposed to play around with this formula. So you can make d the subject by cross multiplying. That is going to be 20 by 0.1 squared. So that's 20 by 0.1 squared is equal to d squared times 0.6, which is 0.6 d squared, divide by 0.6 here, divide by 0.6. So that was going to cancel. So d is going to be given. In order for you to remove the square, you're going to introduce the square root of this. All right, so it's going to be the square root of this part. So meaning to say our d was simply going to be the square root of this part, which was going to be 0.57735. So that's 577. Remember, we used the diameter on the plunger, this one, in meters. So it means the diameter on the ram is going to be in meters. Also, if you want to convert to millimeters, you can multiply by 1,000. It's a choice. We have the answer already. So that one, it's your choice to do that. So the fluid pressure. So in order for you to calculate the fluid pressure, all right, so remember, pressure is simply taken from force times area. All right, for force over area, not, I'm now taking from force to say force is pressure times area. Pressure is force over area. Then force is going to be pressure times area. Force is going to be pressure times area. All right, so we need the pressure, so you need the force over the area. So it's going to depend, are you going to use the ram or the plunger? So since you have the whole information here that you are already given from the plunger, it's best for you to use that because you obtain exact values. Yes, you can use the ram. I'm not saying it's wrong. You can use this of the ram, but remember, this is a calculated and also a rounded off value. So it's not going to give us the exact answer that is needed, but it will be marked that answer. All right. So I'm just going to calculate from the ram, then from the plunger, then also come and calculate from what? From the ram, the one that we calculated. So from the plunger in this case, since we said this is 6.22, since we said our pressure is going to be force over area, so you're going to have force over area. But remember that the area is given as a pi d squared over 4. So that means our pressure is going to be the force here of 0.6 kilonewton. So there we are supposed to apply the kilo as it. That time it was there's a kilo, so it will cancel, does not affect. But here we do not have two things that we are going to cancel. We're going to use the force as it is in kilonewton. So that's 0.6 times 10 to the exponent of 3 over the area of the plunger, which is pi d squared, pi times the diameter in meters. That's 0.1 squared over 4 in this case. All right, so that's pi d squared over 4. So this whole part is going to be divided by 4. So this is our area. It's a single term. So take note about that. You're going to have this in bracket or just have it as a single term. All right, so that was going to give us the pressure. In this case, we are going to obtain 76,394,373. So that's 373 in pascals. Remember, pressure is given in what? In pascals. Or you can write in kilopascals. That would be 76,394 kilopascals if you want. All right. Or like I was saying, we could have calculated this from the ram diameter here. If we are to consider from the ram in this case, if we were to consider from the ram, it means our pressure was going to be from force over area, just like the previous part. We are going to use the force on the ram in this case. Remember, on the ram, the force is 20 kilonewton. So this was going to be 20 kilonewton here, which is our pressure. 20 kilonewton, 20 times 10 to the exponent of 3 over the area, which is pi d squared over 4. So it's going to be pi times the diameter of 0.577 squared over 4. So like I said, since you are using a rounded off value, you're not going to obtain exact answers, but you're supposed to obtain exact values if you use the exact value as it was, not a rounded figure. Truly, you are going to have the same answer, but because we are using a rounded off value, this was going to give us 76,487,152 in pascals. You can even convert to kilopascals, divide by 1,000. So as you can see, these answers are just familiar, but not that exact, because here we're using exact values that were given on the question. Here we are using a rounded off figure, but the answers are in the same interval or in the same range. So this is one and the same thing. That's what I'm trying to say. All right, so that is it. That is it. Let's check the other part of the question here on still on question 6. All right, let's check here. So remember here I've got question number 6.3. The following data refers to a single acting hydraulic press again. All right, the ratio between the diameter of the flange and piece. So we are back again on the hydraulic press in this case. So this is 6.3. Let us just try and take our information. So again, we are considering the ram and the plunger in this case. All right, so there we are given the diameter that is affecting the ratio between the diameter of the plunger and the diameter of the ram is 1:3. All right, so we've got the plunger and the ram. So here you've got the diameter D and you've got the cap letter D. So they are saying the ratio there between, take note, the plunger and the ram. So we are going to have the plunger to the ram. Okay, that is how we are going to have it, which is what? 1:3. So the ratio there is given as 1:3. What does it mean? It means D is 1, this D is 3. So you can even write as a fraction D over D like this, which is the smaller one, it's 1. The bigger one on the ram, it's a 3. Or I can have it this way, D over D like this. This D is 3, does not change, so it's going to be 3 over, this D is 1, so it's going to be 3 over 1. You can write it in any way that you want. All right, so let us just leave it for now. Let us just leave it here for now. We shall see this later on. Then we are given the hydraulic press displacement of liquid by the plunger piston per stroke is. We are given the volume there on the plunger. The volume 354.257. So this is the volume on the plunger in this case. All right. So on the plunger side, we are given the volume of 354 257. All right, this is in cubic centimeters as we are given there. Then also we are given, if we check, assuming the stroke length of the plunger piston is 70 centimeters, we've got the stroke length, which is our L, or you can write it as H. So this one is up to you. You can write it as L or H, but that's the stroke length there of 70 centimeters. And what else we are given also, and the force applied to the plunger piston is 280 Newton. So if got the force on the plunger, everything here is on the plunger. So if got the force of 280 Newton. So remember, here it's our stroke length, which can be L, or it can be given as H. So that is the information that we're given. And from this information, the question is asking us to calculate the mass in liters. So we need to calculate the mass in liters that can be raised. All right, that can be raised. That is the most important thing. Can be raised. Where? Remember, the plunger is the one that is pushing up the ram. So the ram, as it is going up, it is the one that is being raised. So we are supposed to calculate the mass from this side. We are supposed to obtain the mass from what? From the ram in this case. But it is supposed to be in liters. So there's no effect because we understand that a kg is equivalent to a liter, 1 liter in this case. So it's a 1:1 ratio. All right, but the question is, how are we going to obtain this mass from the part that was being raised? As we are considering from the ram, it means what we need from the ram in this case is going to be the force. We are going to need the force that is affecting the ram, since we know that the force is equivalent to mg. All right, so this is 6.31. Let me just write it this way. So since we know that the force is equivalent to the mass times the gravitational acceleration, so we can calculate the mass from there, which is force over the gravitational acceleration. But we do not have this force on the ram. We have it on the plunger, but it is not the one that is raised. It is the one that is raising the plunger. So we can't calculate it from here. No, this is wrong. We are supposed to calculate it from the force on the ram. So meaning to say we are forced to calculate what? We are forced to calculate F, which is the force on the ram. Just like what we did in the previous case where we calculated diameter. Remember, I said we can use the formula that is relating these two. That is the force on the plunger of the diameter of the plunger is equal to the force on the ram. This is our ram. This is our plunger. The force on the plunger over the diameter squared of the plunger. So since we have to calculate this F on the ram, we can simply remove this d squared here by multiplying both sides by what? By d squared. So this will cancel, meaning to say we are going to be left with the force on the plunger, which is going to be F over d squared times d squared. All right. So this here, what does it mean? It means we've got d squared over d squared like this. So this is the force. Let me write it this way. It's going to be force times d squared over d squared. D squared over d squared. Why am I trying to? Because we do not have these diameters. We are given a ratio. So you are supposed also to write in a way that you understand in terms of what the ratio that you are given. Since you have got d over d, this one, the ram over the plunger, meaning to say we can write it in the same way. Remember, these two, they are being squared. So it simply means we've got the force times d over d like this, everything being squared. Everything is being squared. That is what it means there. And like I said, from this, we can play to have d over d like this, which is 1 over 3, or you can have this one of the ram to the plunger, which is 3 over 1. You use the one that is exactly displayed here. We need the plunger to the ram, and this is the one, the plunger to the ram, which is 3 is 1, the plunger, which is 3, the ram, which is 1. So be careful when you are substituting there. So our force on the ram is going to be the force on the plunger, which is 280 multiplied to the ratio. Now we are inserting the numerical values because we are given a ratio of ds to d, which is 3 over 1. So it's going to be 3 over 1 squared. So that's it. You're done. You're going to have your force in this case. So the force on the plunger in this case was going to be 2,000 520 Newton. With this force that we have obtained here, we can obtain the mass that we are being asked here, because that is the one that was being raised, our ram in this case of 2,520. And we said before, the mass is going to be the force on the ram over the gravitational acceleration, and we calculated this. So we're going to have the mass as the force on the ram. Remember, we got 2,520. So it's going to be 2,520 over the gravitational acceleration of 9,8. So this is going to give us the mass, which is going to be 257,143 in kilograms. But remember, we are asked to give our answer in liters. That's why I talked about this conversion. A kg is equivalent to 1 liter. So it simply means, therefore, our mass, because it's a 1:1. If this is 1, this is 1. So it means if our mass is 257, therefore it means our mass is also 257,143 in what? In liters, because it's a 1:1 ratio. If this is 1, this is also 1. So if this is 2, this is also 2. That's a 1:1 ratio. All right, that's it. Calculate the diameter of the plunger piston. We are asked to calculate the diameter of the plunger in this case. All right, let's check what we have. They've got the force, there's nothing. The mass, there's nothing. All right, let's consider here. Since we are to calculate the diameter of the plunger in this case, there we are given on the plunger, we've got the volume, and we also have the stroke length. All right, so let's play around there, because remember this formula here. Let me just try to erase this part. Remember, the volume is taken from the product of these two. The product of these two gives us what? Gives us the volume. The product of what? The area and the stroke length. All right, so let me write it down. 6.32. From the plunger in this case, remember, a given volume, and volume is equal to area times the stroke length, which is the height. If we can calculate the area, it means we can calculate the diameter, isn't it? Because we know that, okay, let me explain here. Like I'm saying, if we can calculate the area, we can calculate the diameter, because under that the area is equivalent to pi d squared over 4. And we can calculate the diameter from there, make d the subject, let us cross multiply. That's 4 times a, which is 4a, is equal to 1 times pi d squared, which is pi d squared divided by pi, both sides. So that means d squared is going to be 4a over pi. So to find d, simply introduce the square root to remove the square. So that d is going to be the square root this side, the square root that side. So we're obtaining the answer from the area as 4a over pi under the square root. This is the formula that we are going to use for the diameter if we have the area. If we have this area. So it means we are supposed to calculate area from here. So let us calculate area. How can we calculate area? We have the volume and the height. So we can make area the subject, divide by the height. This will cancel. So our area is going to be given as the volume over the height, which is our stroke length. So our area, we have the volume here, 354,257 in cubic centimeters over the stroke length of 70 centimeters. So that is going to give us our area in square centimeters in this case. So we are going to obtain our area as 5.061 in square centimeters. But that is not our answer. The question is to calculate the diameter. But since we have a relationship that we talked about here from the area to the diameter, that the diameter is simply the square root of 4a. So therefore, it follows that our diameter is going to be the square root of 4 times the area, which is 5.061. Remember, this is square centimeters. So our diameter is going to be in centimeters, all right, over pi. So that's it. You're going to obtain your diameter from that on your calculator. So our diameter is going to be what? All right, sorry for that. Let me just change here. All right, so our diameter is going to be given as a decimal, which is 2,538, and centimeters there on our units. So that is the diameter. If you used meters, your answer is going to be in meters. If you used millimeters, your answer is going to be in millimeters. That is the case. All right, so that was it here, the diameter of the plunger piston, 6 marks for everything, then 12 marks here. Question number 7, it was on electricity. All right, define the volt. Remember, the volt is just, we're talking about the potential difference between 2 points on a conductor, but it must carry 1 amp and also have a resistance of 1 ohm. All right, so let me just have this in word. So we are simply saying the potential difference between 2 points, all right, between 2 points, all right, between 2 points, that's a 2 points there, on a conductor, all right, then carrying 1 amp of current, all right, carrying 1 amp of current when the resistance is 1 ohm. When the resistance in this case is of when the resistance of the conductor, was referring to the conductor in this case, the resistance of the conductor is 1 ohm. So that's the definition of a volt, which is simply current times the resistance. To have 1 volt, must have 1 amp and 1 ohm to have a 1 volt. That is to define a volt in this case. All right. So that was our question. 1 mark. Just know your theory and know your theory very much. Then you're given 7.2, which is 3 cells with an EMF of 2 volts. So if you've got 3 cells here, the EMF there is 2 volt in series, and 0.1 ohms resistance, internal resistance in series. So it means we are going to obtain the total EMF, because this is given, they are in series, 2 volt, 2 volt, 2 volt. So we're going to add, which is simply 2 times 3, which is 6 volts from this information. So the whole of this part that we are having there, the voltage or the EMF is 6 volts. All right. Then the internal resistance of 0.1, each connected in series. So meaning to say our R is going to be 0.1 times 3 of them, which is 0.3 ohms in this case. So this will be our total internal resistance of 0.3 ohms. That was the case. So the question now is calculate the equivalent resistance of the circuit. All right, we have to calculate the equivalent resistance of the circuit. So if we are to consider our circuit in this case, the total resistance, that's 7 point, all right, this is 7.21. Okay, 7.21. So you're gonna have the total resistance. So here, since you are not given, say this is R1, yes, you can have it as R1, R2, but let's just see, guys. We are going to add the internal resistance in series with this, in series with this. But here we are having what? A parallel combination, which is gonna use the product over the sum. So that's it, guys. We have got the total resistance there. So we are going to obtain 0.3 for the internal resistance. There are 3 of them, each of 0.3 ohms, 3 of them, all right, plus 0.8 plus the 3 ohm here, plus the parallel circuit. So RP in parallel, remember 2 resistors in parallel, it's product over sum. So it's 6/9 over 6 plus 9. So this is for our parallel combination. This is our RP. So let's just calculate our RP. You never know, we might need this value later on. So if we calculate here, we are going to obtain 3.6 from there. The product of the 2 over the sums is going to be 3.6. So that's it. We have got the total resistance of the circuit. Add everything. This is going to be 7.7 ohms. All right. So that was going to be the total resistance, the total resistance of our circuit. All right, then let's check the other part. Now we are given to calculate the reading on the ammeter. So remember, the ammeter, it measures current. So you're supposed to calculate the current there. All right. So on our ammeter, this ammeter is connected in a connection where it measures the current of the whole circuit. So it means you are supposed to calculate the total current there. That's the reading on the ammeter. The ammeter measures what? Measures current. So that means there we are supposed to calculate the total current, 7.22. So the total current, which is voltage over the total resistance. And the voltage here, we're talking about the total EMF in this case. So that is, we are going to have the total EMF. We say it here, it's going to be 6 from the calculator that we did here. So we're going to have 6 volts over the total resistance. And we calculated the total resistance, 7.7. So that was going to give us the total current of the circuit. This is the current measured by the ammeter, which was going to be 0.779 amps. Okay, so we've got the total current, then the reading of the voltmeter, V1 and V2. All right, so let's check our diagram. Remember, now we have got the current flowing in the circuit of, from what we calculated, we got 0.779 ohms. So having this current, we are supposed to calculate V1 and V2. In this case, the voltage at V1 and V2. V1 is the one that is in parallel. This is the voltage across the parallel combination. So you're simply talking about VP in parallel. So it's just going to be the current times the total resistance in parallel, because we have a current flowing and we also calculated this total resistance in parallel. Remember here, we calculated in parallel. This was the resistance in parallel. We got what? 3.6 from this product over sum. So we're going to take the resistance in parallel, 3.6. All right, so meaning to say V1, that's 7.23 in this case. So V1 is simply equal to VP in parallel, which is the current times the resistance in parallel. So you can just have as the total current times the resistance in parallel. So that's our V1, of which we've got the current flowing, 0.779. So we've got 0.779 times the resistance that we got in parallel, which we calculated here. Our RP, it was 3.6 from the product over the sum. So you're gonna use 3.6 there. All right, so that's going to be our V1. So meaning to say our V1 was going to be something like 2.804 volts. All right, that's it. Then V2, remember it's V1, V2 is here across the 3 ohm. So here's just current times resistance, all right? Because here we do not have anything in parallel, so just gonna have it direct. So meaning to say for V2, we are simply going to multiply the current of 0.779 times the resistance that is affected there, which is the 3 ohm. The resistor across is 3 ohm. So we are going to multiply by the resistance. Current times resistance, we get the voltage. So that's the reading on the voltmeters, which is going to be 2.337 volts in this case. All right, so that was how we're supposed to attempt these typical questions. All right, let's check the other part. All right, so that was it here. 4 marks for that. And the current through the 9 ohm resistor, the 9 ohm resistor, where is the 9 ohm? The 9 ohm resistor is the one that is in parallel. So since we said in parallel, the voltage is the same. Remember, in parallel, voltage is the same. And we calculated V1 in this case. Remember, V1 was 2.804. So there's a voltage here. There's a voltage in parallel of 2.804 volts. And this voltage is the same. So we are simply going to use voltage over the resistance there. We find the current. That's it, voltage over resistance. So the voltage in what? In parallel over the resistance of the 9 ohm. So that's 7.24. The current across the 9 ohm is going to be the voltage in parallel of 2.804 over the current that is flowing. What you're supposed to, sorry, you need the current over the resistance also, that we find the current. So we are going to divide by the resistance in this case, so that we determine the current. Sorry for that. All right. Sorry for that thing. Okay, so it's gonna be 9 like this. All right. So that's the current across the 9 ohm was going to be 0.312 amps. Okay, so that was going to give us the value of the current across the 9 ohm. So please, let's cross-check our circuit. Okay, that's it, 9 ohm. All right, so we're done there. Let's check other part of the question. We are also given 7.3. This part we are given a single phase transformer has a supply voltage of 240. So we have got a single phase transformer. Supply is on the primary, so VP is 220 volts. Secondary voltage on the secondary side, we've got 9 volts. And the power at full load is given as 20 watts. And this is a single phase. Remember, on a single phase, we simply talk on a transformer as the voltage times the current in this case, okay? So, or at full load. And if you're considering on the primary side, the question was to calculate the power or the primary current at full load. So we are simply going to use voltage times current since we've got the power, and we know that the power is equivalent VP times IP, and we need the current. So the power is 20 watts, the voltage on the primary, 220 times the current on the primary. So the current on the primary was going to just divide by 220, divide by 220, there this cancels. So it's gonna be 20 over 220. That was going to give us the current in the primary. And if we divide, we are going to obtain 0.090909 like that. All right, which is going to be 0.091 to create a small base in amps. All right, so that's it. 2 marks for that. As you can see, chemistry part on question number 8, we're being asked to distinguish between reduction and oxidation. All right, so as we know that reduction, there's a reducing part there. All right. So then oxidation there, in terms of electrons, reduction is simply a gain of electrons, while oxidation is a loss of electrons in this case. So something is gaining and something is what is losing. So each and guys, if you are dealing with chemistry, don't think that it's the chemistry that you worked with at grade 12. No. It's not like that. It's not like that. The chemistry part is simply, what can I say? It's simply the basics that you are supposed to understand. The basics that you are supposed to understand. All right, so like I said, reduction is going to be the gain of what? Is simply the transfer of electrons between species in chemical reaction, where the process is of gaining electrons or a decrease in oxidation state by the element. So we are simply saying this is the gain, all right, is the gain of electrons. In this case. So since we are comparing, we are going to just say while oxidation is the loss of electrons, all right, is the loss of electrons. Just like that. All right, 2 marks for that. Name all the elements that make up the compound sulfuric acid. All right, the compound sulfuric acid is given by H2SO4. So the compounds that we are talking about there, we are referring to the hydrogen. So there, as you can see, there is hydrogen, there is sulfur, and there's also oxygen. So these are the ones that we are supposed to be having on our answer. 8.3, give the chemical formula for calcium carbonate. So calcium carbonate, that's CaO3. That is our calcium carbonate in this case. So the chemistry part, we just hope as time moves on, we're just going to talk about the whole part of our chemistry, what you are required to understand in your syllabus. Like I said, it's not a big deal. this part of chemistry. You just need to understand the basics, not like to know the chemistry thing. No, just the basics that you're supposed to understand. So we shall see as we move on as a family, but let us try to engage with others, share our videos to your other friends, encourage others also to subscribe to our channel, and also become a member so that you have access to all the videos that we shall be having at Medzone African Motives. But for now, till we meet again.